Okay, dear students, welcome back to the class. Last class, we ultraviolet visible spectroscopy basics. Today we are going to continue the same thing. We are going to discuss a bit more detail about the basics of ultraviolet visible. We second semester പഠിച്ചു. So അതുകൊണ്ട് തന്നെ ഇതിന്റെ ഒരുപാട് ഡീറ്റെയിൽസിലോട്ട് dive ചെയ്യാനായിട്ട്. So ഇവിടെ നമ്മൾ if we have an absorption spectrum, electronic absorption spectrum that originates because of transitions between the HOMO and the LUMO of a molecule, and for some reason the spectral intensity, that means the peak height at the spectral maximum, increases or decreases, or if the peak maximum shifts either towards lower energy or towards higher energy, we could say that the electronic spectrum is being influenced by some factor that affects the molecular structure of a molecule. അതായത് എന്തെങ്കിലും ഒരു ഫാക്ടർ മോളിക്കുലറിൻ്റെ സ്ട്രക്ചറിനെ ഏതെങ്കിലും രീതിയിൽ ഇലക്ട്രോണിക് എക്സൈറ്റസ്റ്റൈലിലുള്ള മോളിക്കുലർ സ്ട്രക്ചറിനെ ഏതെങ്കിലും രീതിയിൽ ഏതെങ്കിലും ഫാക്ടർ അഫക്റ്റ് ചെയ്യുകയാണെങ്കിൽ ദാറ്റ് കുഡ് റിസൾട്ട് ഇൻ either an enhancement or decrease in the spectral intensity, or could result in a shift of the spectrum towards either lower energy, that means higher wavelength, or towards lower wavelength. ഇങ്ങനെയുള്ള സ്പെക്ട്രൽ ഷിഫ്റ്റിനെ നമുക്ക് നാലായിട്ട് കാറ്റഗറൈസ് ചെയ്യാം. നമ്മൾ സെക്കൻഡ് സെമിസ്റ്റർ കണ്ടതാണ്. If the spectral intensity or the absorbance, we have got the absorbance or the molar extinction coefficient along the y-axis here. So if the spectral intensity increases, then we call the effect as a hyperchromic shift. The spectral intensity decreases, we call the effect as hyperchromic effect. The spectral intensity, if the spectrum shifts towards the longer wavelength or towards lower energy, the effect is being called bathochromic shift. The spectrum shifts towards the higher energy or shorter wavelength, we call the effect as being hypsochromic shift. So ഇങ്ങനെയുള്ള 4 effects ആണുള്ളത്. We are going to or we have already seen what effects could be due. We are going to just recall those what we have learned in the second semester. The bathochromic shift, or in other words we call this one as red shift, because the spectrum is being shifted towards the red region, the visible spectrum. In this case, the spectrum shifts towards the longer wavelength or lower energy. This could be happening due to an increase in the polarity of a solvent. We shall be seeing these effects later. Or correspondingly, an increase in the attractive polarization forces between the solvent and the absorber, which we have already seen in the second semester. We have seen the Lippert-Mataga equation and the Lippert-Mataga plot, which represents the interaction between a solvent and the absorbing molecule. And then the next effect is hypsochromic shift, and since this shift happens towards shorter wavelength or towards the blue region of the visible spectrum, we call this one as blue shift as well. So in this case, shift could happen because of better solvation of lone pair electron density, for example on a heteroatom in the molecule, which happens by virtue of an increase in the polarity of the solvent. So basically bathochromic shift solvent polarity increase ചെയ്യുമ്പോൾ സംഭവിക്കുന്നു. ഇവിടെ അത് അങ്ങനെ ഷിഫ്റ്റ് ഉണ്ടാകാൻ കാരണം സോൾവെൻറ്റും അബ്സോർബിങ് മോളിക്യൂളും തമ്മിലുള്ള അട്രാക്റ്റീവ് എഫക്ട്സ്, പോളറൈസേഷൻ എഫക്ട്സ് കൂടുതൽ ഫീസിബിളായിട്ട് നടക്കുന്നതുകൊണ്ടാണ്. അതേസമയം ഹിപ്സോക്രോമിക് ഷിഫ്റ്റ് എന്ന് പറഞ്ഞാൽ blue shift. That could also happen with an increase in the polarity of the solvent. But in this case, our non-bonding electron density better solvation നമ്മൾ ഈ effects കാണാം. Okay. If you consider the non-bonding electron density, for example, in a particular system, carbonyl system, C double bond O, carbonyl system നമുക്ക് oxygen non-bonding electron density, which we can represent by the non-bonding orbital n, and then we have got the pi molecular orbitals in carbonyl system. So obviously we have got a pi star molecular orbital. We can have or we may have a non-bonding to n2 pi star electronic transition carbonyl system. So this one is a forbidden transition, and correspondingly we see a very weak band in the electronic absorption spectrum because it's symmetry forbidden. But sometimes because of breakage of symmetry, we might see a little bit of enhancement of the intensity of n2 pi star transition. So we usually see a weak broad band, the electronic absorption spectrum, corresponding to the n2 pi star transition. So for example, if you take a typical model system, molecular system, in which we have got a carbonyl functional group, then we can represent the molecular orbitals of the carbonyl system by the pi and pi star molecular orbitals, because we have got C double bond O and we have got pi and the pi star molecular orbitals, and then we have got non-bonding electrons on the oxygen atom. So this picture, this energetical picture represents the energy levels of the molecular orbitals of carbonyl system in a molecule which is being dispersed in a nonpolar solvent. So a nonpolar solvent doesn't stabilize either the pi or pi star molecular orbital or the non-bonding orbital, the carbonyl system, to a great extent. Whereas if you dissolve the same molecule which contains the carbonyl functional group in a polar solvent, for example methanol, then what happens is the pi molecular orbitals usually have got the same energy, whereas the pi star molecular orbital, which is a bit more diffused in space corresponding to pi molecular orbital, in a sense that results in a polarization of the pi star molecular orbital compared to the pi molecular orbital, which is symmetric with respect to carbon oxygen bond. So pi star is more polarized compared to pi molecular orbital. So the more polarized pi star orbital will be much more stabilized by the polar solvent because of electrostatic or polarization interaction between the polar solvent and the polarized pi star molecular orbital. So this results in a slight lowering of the pi star molecular orbital in polar solvent compared to non-polar solvent. Whereas compared to the case in here, the non-bonding orbital of the oxygen, which is by the way directional, which has got a direction, will be better encapsulated by the polar solvent molecules, which could result in a better interaction, polarization interaction between the non-bonding orbital of oxygen with the polar solvent molecules, resulting in better stabilization of the non-bonding electron density on the oxygen atom. So altogether, this polarization interaction between the non-bonding electron density on the oxygen atom with the polar solvent results in a stabilization of the non-bonding orbital compared to the case in a non-polar solvent. The non-polar solvent doesn't stabilize the non-bonding electron density on the oxygen atom as much as the polar solvent does. So now if you compare the n2 pi star transition, you can see that this much is the energy difference between the non-bonding orbital and the pi star orbital, whereas in a polar solvent the energy difference between non-bonding and pi star orbital is much greater. So obviously, for the same molecular system taken in a non-polar solvent and a polar solvent, the end-to-pi transition will be much more blue shifted in a polar solvent compared to the case in a non-polar solvent, because the transition requires greater energy in a polar solvent compared to polar solvent. So this is the opposite of pi to pi star transition. You can see in a non-polar solvent, this much is the energy difference between the pi and pi star molecular orbitals in a non-polar solvent, whereas in a polar solvent the energy difference is slightly reduced. So the energy difference is lesser. As a result, the transition will occur at a lower energy in a polar solvent for pi to pi star transition. So the take home message is, when you increase the polarity of the solvent, the pi to pi star transition will be occurring at a lower energy or a greater wavelength. Whereas when you switch from a non-polar solvent to a polar solvent, the n to pi star transition will be shifting towards a higher energy or a shorter wavelength. So in other words, in polar solvents, pi to pi star transition will be redshifted, whereas in polar solvents, n to pi star transition will be blue shifted. So in polar solvents, pi to pi star transition is redshifted, whereas n to pi star transition is blue shifted. So this one is a typical example where we take the absorption spectrum of this typical molecule, mesithyl oxide, in two different types of solvents. So one of them is heptane, which is a non-polar solvent, and the other one is methanol, which is highly polar compared to heptane. So here you can see this one is the actual electronic absorption spectrum, and you cannot see much of the bands in here. So this spectrum represents a zoomed in version or enlarged version of the original spectrum in this particular region. So you can see that there is a very weak broad band here, which has got an absorption maximum around 325 nanometer. So obviously this one represents the n to pi star transition of the carbonyl functional group in mesithyl oxide, and this large band in here, or this band going up all the way up here, represents the pi to pi star transition of the carbonyl as well as the pi pi star system in here. So you can see the absorption maximum of the n to pi star transition is around 325 nanometer. So if you take the spectrum, the same compound in a much more polar solvent, you shall be able to see that this absorption peak corresponding to the n to pi star transition shifts its absorption maximum from 325 nanometer to say around 310 nanometer. So here the absorption maximum was at around 325 nanometer, but in a polar solvent comes around at 310 nanometer. So obviously for the same molecular system, the n to pi star transition shifts from 325 to 310 nanometer in a polar solvent. So you get a blue shift. This table shows the transition energies, both the pi to pi star as well as the n to pi star transition energies of mesithyl oxide in different solvents having different polarities. Here we have got hexane as a first solvent, then diethyl ether, methanol, ethanol, methanol, and water. So hexane is a non-polar solvent. Diethyl ether is slightly polar compared to hexane. Ethanol is polar. Methanol is again much a bit more polar. And water is the most polar solvent, particular set of solvents. So you can see that as you go down along this table, the polarity of the solvents increases. And here these values in here represents the absorption maximum of pi to pi star transition. You can see that in hexane it's around 229.5 nanometer, whereas go down the table, the P gets shifted towards longer wavelength. So you get around 244.5 nanometer in the Morse polar solvent. So this is expected as based on the theory we have already discussed. In nonpolar solvents, the pi to pi star transition energy is much greater, whereas in polar solvents, the pi to pi star transition energy is getting reduced. But if you compare the absorption maximum of n2 pi star transition of the carbonyl functional group here, you shall be able to see that for hexane, the absorption maximum comes around 327 nanometer, whereas as you go down the table, the absorption maximum decreases towards shorter wavelength or higher energy. So that this represents a blue shift, progressive blue shift of the absorption maxima as you go down from hexane to water. So this is again, or this fits really well with the theory we have already discussed. Any part of a molecule which can absorb radiation and undergo transition so as to impart some color to the molecule, if the transition occurs in the visible region of the electromagnetic spectrum, are called chromophores. So we have this table lists some of the chromophores starting from CH, and these are typical examples of the compounds that could be containing the chromophores on the left hand side of the table, and these are the possible electronic transitions that could be associated with this chromophores, and these are some of the typical absorption maximum values of the transitions in this chromophores. And the last member in this table is the molar extension coefficient associated with this typical transitions here. So you can see that we shall be seeing electronic transitions mostly associated with C double bond C, then C double bond C, such as in allyl system, then C triple bond C, then CO, En, CS, C double bond O, then the carbonyl functional group system or C double bond in different functional groups, then C double bond N, C double bond N, N double bond N, N double bond O, and so on. These types of molecular systems. And you can see that in CH we have nothing but sigma molecular orbitals, so the possible transitions are sigma to sigma star. In CC as well we get only sigma to sigma star transitions, but in C double bond C, in addition to sigma molecular orbitals, we have got pi molecular orbitals, so we have got the possibility of pi to pi star transitions in this system, which occurs at 103 nanometer. Then again, the allyl type system, we can have pi to pi star transition that usually occurs at 170 nanometer. See the difference here, we have got only one single bond here, and the pi to pi star transition occurs at 103 nanometer, whereas when we have two double bonds in conjugation, the pi to pi star transition happens at a higher wavelength. So we shall be seeing the reason for this effect later. And in CO we could have N2 sigma star transition because we have non-bonding electron density on the oxygen, which could be getting promoted to the sigma star molecular orbital between the carbon and the oxygen, which occurs at 180 nanometer. Then carbonyl system in different functional groups, where we can have N2 sigma star transitions, then pi to pi star transitions, and N2 pi star transitions. If we have halogens directly bonded to carbon, then we can have N2 sigma star transition that could happen between the non-bonding electron density on the halogen towards the sigma star molecular orbital between carbon and the halogen. These are again some typical examples of chromophores. The first one is N-heptene, an example of an alkene. So here the pi to pi star transition could be happening at 177 nanometer. Then a typical alkyne, we could have the transition pi to pi star transition occurring at almost the same energy. In carbonyl, again, like we have seen in the last table, we could have n to sigma star and n to pi star transitions, as well as we could have pi to pi star transition. So you can just go through these tables. I hope you can understand what we are talking about here. So if we have any doubts, we can clear it in the class. Okay, so why do we study electronic transitions in functional groups? Because electronic transitions happen between molecular orbitals, which are states having discrete energies, and as you know, transitions between states having discrete energies can be classified as quantum transitions. So depending upon the energy gap between the molecular orbitals, the transitions energies could vary. And for similar functional groups, say for example, functional groups which have got almost the same molecular structure or similar molecular structure, could undergo electronic transitions between states having almost similar energies. So the transition energies would be mostly same for these similar functional groups. Whereas if you consider two dissimilar functional groups, two different functional groups, which have got entirely different electronic structures, then the electronic transitions between the molecular orbitals in these two different functional groups will have different transition energies. So the electronic absorption spectrum corresponding to the electronic transitions in these two different functional groups will obviously occur at two different energies, or you shall be seeing the absorption peaks at different energies or different wavelengths. So in a sense, we can characterize the electronic structure or the nature of these functional groups by studying the electronic absorption spectrum or electronic absorption spectra that arose from electronic transitions between the molecular orbitals in these functional groups. So that is the reason why we use electronic spectroscopy in order to elucidate the structure of functional groups and molecular for molecules, any molecule. So any functional group that is capable of having a characteristic electronic transition. So characteristic in the sense, the functional group that is capable of undergoing electronic transitions between well-defined discrete molecular orbitals is called a chromophore. So in a sense, the literal meaning of chromophore is color loving system. So here the color loving system or color loving group is the functional group that undergoes electronic transitions. So any factors that could influence or change the structure or the electronic properties of the chromophore will obviously change the nature of the molecular orbitals of the involved in the chromophore, as well as the energies of the molecular orbitals that are being a part of the chromophore, and that could change the transition energies in the chromophore, that could influence the electronic or change the electronic absorption properties, electronic absorption spectral properties of the chromophore. So in a sense, any molecular system that could undergo electronic transition, which is essentially a chromophore, and any factor that could change the transition energy of this chromophore could be studied using electronic absorption spectroscopy or UV visible absorption spectroscopy. So we shall be studying a couple of organic chromophores. We will start with alkanes, and simple alkanes possess only sigma bonds. There are no pi bonds or non-pair electron density, and we have got only sigma and sigma star molecular orbital. Here this picture shows the in-phase overlap of the 2p orbitals on 2 carbons in a normal alkane, which results in a sigma molecular orbital. And here we see the out-of-phase overlap of the 2p orbitals on the carbons, resulting in a sigma star molecular orbital. in alkane. So normally, as you see, the 2p orbitals will occupy the lowest energy sigma molecular orbital, and when the system is being irradiated with a suitable ultraviolet radiation, which happens in around 100 nanometer or like that, then one of the electrons can be excited from the sigma molecular orbital to the sigma star molecular orbital. So this one is basically a sigma to sigma star transition, which usually occurs in the ultraviolet region. And then another type of chromophore would be a heteroatom being directly bound to a carbon atom, such as the ones in alcohols, ethers, amines, and sulfur compounds. In alcohols, we have got oxygen directly bound to a carbon, and it's the same thing in ether. In amines, we have got a nitrogen directly bound to a carbon. Then we have got a sulfur, this being directly bound to carbon. All these heteroatoms are being bound to carbon via a sigma bond, and these heteroatoms carry non-bonding electron density. So assume that there is a carbon heteroatom sigma bond, and there is a non-bonding electron density on the heteroatom, and in that particular case we have got sigma molecular orbitals and sigma star molecular orbitals. Here the sigma, for example, if you consider the bonding between a carbon in an organic molecule, a part of an organic molecule, with a nitrogen, for example the one in an amine, NH2. So in that particular case, you can assume that the sigma bond is being formed by in phase overlap of the 2p orbitals on carbon and the 2p orbitals on nitrogen. Okay, so that results in a sigma molecular orbital, whereas the outer phase overlap between the carbon 2p orbital and the nitrogen 2p orbital results in a sigma star molecular orbital, forming a carbon nitrogen sigma bond. And then we have got the non-bonding electron density on the nitrogen bond, which doesn't interact with the carbon 2p orbitals here. So here is the energy level of this non-bonding orbital, so which is obviously the nitrogen is sp3 hybridase here. And given that we have given suitable energy to the molecular system, we can induce either sigma to sigma star transition, and if you supply a little bit lesser energy that satisfies the energy difference between non-bonding orbital and sigma star bonding orbital, then anti-bonding orbital, then we could induce N2 sigma star transition. So basically you can consider N2 sigma star transition as being a transition between the non-bonding electron density on nitrogen to the sigma star anti-bonding molecular orbital on the carbon nitrogen bond. Okay, so this is how N2 sigma star transition happens in alcohols, ethers, amines, and sulfur compounds. Then alkenes and alkanes. Obviously, you know, we have seen in Huckel molecular orbital theory, in alkenes and alkanes, in addition to sigma molecular orbitals, we could have pi molecular orbitals as well, which happens or which arises out of sideways overlap of 2p orbitals on carbons on that forms a bond, as you know it. So here this one is a simple picture of ethylene, where two carbon atoms forms a sigma bond here, and two 2p orbitals on carbon, for example 2p y orbitals on carbon, two adjacent carbons, when they overlap sideways or lateral overlap, if that happens in phase, then we have got a pi molecular orbital, and if the overlap happens out of phase, then we have got a pi star molecular orbital. So we have got a node here, and obviously the 2p orbitals will occupy in the lowest energy molecular orbital, which is the pi molecular orbital, and if you give enough energy to induce transitions between pi molecular orbital to pi star molecular orbital, then a one electron transition can happen, resulting in a populating the pi star molecular orbital. So this one is nothing but a pi to pi star transition, which is usually being observed for non-conjugated alkene or alkane systems at around 175 and 170 nanometer. respectively. And one of the most celebrated cases in electronic spectroscopy is carbonyls, because mostly our molecular system, organic molecular systems usually contain carbonyls, most like aldehydes, ketones, esters, acids, and so on. So uh, this one is a very interesting molecular system where we have got both the pi to pi star transitions and n to pi star transitions are feasible. But as we have said already or discussed already, the n to pi star transition is forbidden by selection rules, but it could happen very weakly, whereas the pi to pi star transition is highly allowed, and that could happen in the ultraviolet to visible region, depending upon whether the molecular system is conjugated or non-conjugated. So in carbonyls, we have got, say for example, if you see the carbon oxygen bond here, sigma bond here, the 2p orbitals on carbon and oxygen could overlap in phase to form a pi molecular orbital, and if the overlapping happens out of phase, then we have got a pi star molecular orbital. And the 2p orbital on oxygen that lies out of plane with the 2p orbital on this particular 2p orbital on carbon is actually a non-bonding orbital, and the energy of this non-bonding orbital happens to be around here. And then if you give sufficient energy by means of radiation, then transition can happen between pi to pi star, and then it could you give a little bit lower energy, so that if you could induce transitions between n to pi star, then transitions can happen between the non-bonding electron and oxygen to the pi star molecular orbital here. So in general, pi to pi star transitions are highly allowed or feasible transitions in ultraviolet and visible spectroscopy, and whereas n to pi star transitions are weakly allowed or forbidden in the usual chromophores that you encounter in electronic spectroscopy. And if you have any substituent attached to the functional groups or chromophores, it could change the intensity or the transition energy of the chromophore. Okay, so some substituent groups, when they're being attached to the chromophore, could change the intensity of the electronic transition, or the transition energy of the electronic transition. Such substituents that could increase the intensity, and sometimes that could change the wavelength of the absorption, are called auxochromes. Okay, auxochromes are not chromophores. Auxochromes doesn't undergo transition on its own, unlike chromophores. Chromophores undergo transitions on its own, whereas auxochromes doesn't undergo transitions on its own in the spectral region where the chromophore absorbs the radiation. So common auxochromes are usually alkyl, hydroxyl, alkoxy, and amino groups, and halogens. These are auxochromes that could influence the electronic absorption spectral properties of chromophores.